Hello everyone! Welcome to this video on using a neural network to solve a dataset generated from a computer simulation of an epidemic outbreak. We will be using the Keras library in Python to create our neural network model and see how it can help us find the most effective parameters for containing an outbreak. The generated dataset simulates the spread of an epidemic, and we will use the neural network model to analyze the data and make predictions on how the outbreak might progress. By training the model on this data, it can learn to recognize patterns and make accurate predictions about the potential spread of the disease. First, we will see what a neural network is, then explain how the simulation works, and finally, the implementation and use of the neural network. This video is intended for a beginner audience, so even if you have little to no experience with neural networks or programming, you should be able to follow along. If you have any questions or need further clarification on any of the concepts discussed, please feel free to ask in the comment section. Let's get started. The field of artificial intelligence emerged from the desire to create machines that can mimic the functioning of biological neurons. These computer neurons are called perceptrons. We will see in more detail how they work and how they are arranged to form a network. A perceptron is an activation function with its multiple parameters weighted by weights, as well as a bias variable. The inputs and weights can be visualized as two vectors. This results in a mathematical equation. We will then assemble each perceptron of layer n with those of layer n-1 for its inputs, creating a network as illustrated here. This network takes as input the data we will be given to the model and as outputs the prediction it makes using the input data. Once we know how to define a perceptron, we can then define all the perceptrons of its layer, resulting in this matrix equation. The weight matrix of the layer is multiplied by the vector of perceptrons from the previous layer n-1, to which the bias vector is added, then the activation function sigma is applied to all of it. This results in the value of the perceptron of layer n. So we have the weights and biases that are variables that we can adjust on each layer in order to train the neural network to respond to our problem. Now, to talk about what an activation function is, it allows the passage of information from a certain threshold. There are many of them, each with its own advantages and disadvantages, but here I will only list the two simplest ones, the rectified linear units function and the sigmoid function. In my program with Keras, I use the rectified linear unit function. In the process of modifying weights and biases, the cost function is important because it will give us the way to modify the network to approach its goal. The errors are the expected outputs of our network. For example, if we are trying to split a point plane into two by a line, the expected answer is then group A or group B. The y's are the outputs of the network. To simplify, the cost function tells us if the prediction is more or less close to the expected value. Our cost function, therefore, has as a parameter the weights and biases of the network. To optimize our cost function, to minimize it, because if we can minimize the costs, it means that our model responds better to the problem given to it, because its outputs are closer to those expected. We will use gradient descent to reduce the cost function. I will not explain the entire reasoning here, but I put in the description all the necessary references on the subject. Similarly to gradient descent, I will not explain the entire reasoning behind backpropagation in this video. However, references will still be provided in the description. But, to simplify, it is simply the method used to adjust all of the weights and biases in order to minimize the cost function. Thus, during the training phase, examples with non-expected outputs must be iterated in order to gradually adjust the parameters of the neural network. For my problem, I asked myself what are the optimal parameters to curb an epidemic. So I programmed an epidemic simulation that we will see in the following. Then I wanted to apply a genetic algorithm that we also talk about later. However, the calculation time was too long with this method. So, how to predict the result of my simulations? That's why I tried using the neural network. My simulation is based on what is called the compartmental model. It allows to simulate the spread of an epidemic according to the following equations. The simplest compartmental model only has three categories: healthy individuals, infected, and recovered, SIR. I have applied this formula in Python and plotted the obtained curves for illustration. For the programming of the simulation, and based on the basic SIR model, I added a category, the vaccinated individuals. I programmed it in C# with Unity for the graphic rendering. It is a simulation that is based on the random movements of individuals within zones. Here, we observe 6 zones, in which individuals move represented by the color of the states. An infected individual can, with a probability, transmit its states during a collision. An infected individual, after a defined period, goes into the recovered state, and an individual in the recovered or vaccinated state can no longer change states. The different parameters that govern the simulation will be explained later in this video. Now, we need to generate the database for training the neural network. My program for collecting data is in Python, and I have an executable for my simulation. It's not the most optimized way, but to connect the two, I coded my own API that communicates between the two through a shared file. All that's left to do is run my simulation automatically a large number of times, collecting both the value of input parameters and the final result of the number of individuals who were infected during the simulated epidemic. This results in a large database in the form of a CSV file that will allow us to train the AI. This database, due to the way my simulation is programmed, needs to be cleaned up. I won't go in detail on how I did it, but I removed any aberrant values. For more information, I've left references in the description. Keras is a Python library that makes it easy to work with neural network, allowing us to more easily implement theory. This library is based on another library called TensorFlow, but in a more simplified way. As you can see in this table, the chosen parameters are displayed, as well as the range of possible values for each one. Number is the number of individuals per zone, percent vaccinated, the percentage of vaccinated individuals among the population, percent quarantine, the percentage of individuals who leave the simulation when they realize they are infected and while they are infected. The infection rate is the probability of transmission during contact. Infection time, the time during which the individual remains in the infected state before moving to the recovered state. The quarantine time is the period of time it takes for the individual to realize they are infected. The travel time is the period that defines the frequency of an individual's random travel between zones. To reduce the required database, we study each parameter independently, assuming that the sum of the models will have the same result as a single model. After training a neural network on one of the parameters of the simulation, here the infection rate, we can observe on the first graph the cost decreasing as the number of epochs increases. The second graph compares the curve of prediction of the number of infected according to the infection rate with the scatter plot of the training data. We can assume here that the model correctly performs its prediction function. I will not display all the curves for each parameter in this video. They are available again in the description. We now have, after training different neural networks for each of the simulation parameters, 7 models which are the trained neural networks. They are simply large functions that take in the parameters on which they were trained as input and predict the number of infected individuals as a result. Now, let's talk about the genetic algorithm I mentioned earlier in the video. It is an algorithmic method that allows finding an optimal solution to a system. Here, our system is a grouping of our 7 models, and we want the algorithm to reduce the sum of the prediction of infections of each model. To do this, we will randomly create a first generation of vectors of the 7 parameters and only select the best vectors, those that give the least prediction number of infections. Make a random part of them change, what we call a mutation, and make some that should not have been selected pass by chance, important for keeping genetic diversity, in order to generate a new generation of vectors by mixing the selected one. Just iterate the process many times. Generation after generations, the input vectors will give predictions with fewer and fewer infections. As we can see, on the first graph, the number of predicted infections decrease as the generation progresses. Additionally, we can see the output of my Python code for implementing the genetic algorithm. The table currently displayed shows the result of this work. The number of individuals by zones should decrease. The percentage of vaccinated or immune individuals should increase. The percentage of individuals respecting quarantine should also increase. The infection rate should decrease. This can be achieved through barrier gesture or other methods to reduce the risk of infection during interactions. To continue, the lower the infection time, the fewer infected individuals in the simulation. Quarantine time should decrease. This can be translated into increased testing in the population. And finally, travel time should increase, which spaces out trips over time, which in the concrete case can be a restriction on geographic movement to prevent individuals from different areas from coming together. Finally, there are several ways to criticize my methodology. The first and most important is the approximation I made by assuming that multiple models for each parameter would behave the same way as a single large model, which is equivalent to considering that none of the parameters depend on each other, which I cannot prove. Additionally, the parameters on which my simulation is based are subjective, and the results are subject to interpretation for each parameter. This concludes my first video. Thank you for watching until here. If you have any questions or recommendations for me, please feel free to leave them in the comment section.